On to section 1.6. Okay, 1.6 is homogeneous systems, subspaces, and bases. So we'll finally define a basis for a vector space. You're usually given vector spaces. I mean, they're described to you in terms of a basis. You're given a basis, and that tells you the types of vectors that are in the vector space. All right, and we're going to encounter systems, more systems of equations stuff, and we're going to kind of tie the two together, tie together our ideas of solutions to systems of equations, along with some ideas involving vectors and vector spaces. Okay, so in this section, more on the structure or the solution set of a system of equations. We'll introduce what we mean by a homogeneous system and relate general solutions to systems of the equations AX equals B, find the general solution. If it isn't unique, then there's free variables and multiple solutions. Relate that to the solution to this type of equation here, AX equals 0. This type of equation here, AX equals 0, the 0 vector, is what a homogeneous system of equations is. So a linear system of equations, AX equals B, is called homogeneous if the right-hand side of all those equations is 0. That is, if the B vector is a 0 vector of appropriate dimensions. The 0 vector is certainly a solution to AX equals 0. It's called a trivial solution. Good news there. Homogeneous systems of equations are always consistent because they always have the trivial solution, for example. Non-zero solutions, other solutions, are called non-trivial solutions. All right, so the question will shift quite often with homogeneous systems from is it consistent or not, of course it is, to questions relating to maybe how many free variables are there, what's the general solution, could still be a topic of interest. Okay. Theorem 1.13 tells us about the solution set of AX equals 0. Not that this is particularly computationally useful. The concept behind it is way elementary. But this will be of use in maybe trying to put a little bit of a geometric interpretation on solutions to systems of equations. We've kind of kept the vectors in one place and had geometric interpretations there. And we had the systems of equations dealt with algebraically and didn't talk so much about geometry there, talk so much about lines and planes and stuff like that, things that you could visualize. Well, we're going to take care of that, and we're going to link together the algebra related to these systems of equations to the geometry related to vectors. Okay, this result simply says, hey, if we consider AX equals 0, the homogeneous system of equations, if H1 through H sub n are all solutions to this system of equations, that is, I could plug in X equals H sub 1 and we get a solution, X equals H sub 2 is a solution, and so forth. Then the claim is any linear combination of those solutions is also a solution. Using H's here for the solutions because we're talking about a homogeneous linear system of equations. Okay, so in the homogeneous case, linear combinations of solutions are solutions. When you like linear combinations, don't you? That's the kind of thing we do with vectors. So it ain't surprising to see it pop up in this setting related to systems of equations. Okay, the proof, like I said, super easy. Hey, if these things really are solutions, H1 through H sub n, then we can take A times H sub 1 and we'll get out the 0 vector. A times H sub 2, get out the 0 vector, and so forth. So if we took matrix A and multiplied it by the linear combination, you know by properties of matrix multiplication, distribution and scalars pull through, or specifically the two properties that we can distribute, really is distribution, because we've got matrix multiplication and vector addition. Distribute the A onto each of those vectors, pull the scalars out front, properties of matrix multiplication. Now we've got R1 times AH1. Hey, but AH1 is a zero vector. So we've got R1 times a zero vector. We got R2 times a zero vector, up through R sub n times a zero vector. That's zero vector plus zero vector plus zero vector. Suppose n times, it's the zero vector. So we plugged in this linear combination for X in a homogeneous system, AX, a alleged vector that's a solution, and we did get out 0. So indeed, this linear combination is a solution to that system of equations. What made it work? 0 plus 0 equals 0. So conceptually, no surprises. The vocabulary is piling up, as it's going to do in this class. Homogeneous system of equations is our new vocabulary word. But hey, the idea behind this was 0 plus 0 equals 0. Okay, let's shift gears a little bit. We'll bring it all together here ultimately and look at subspaces of Rn. All right, a subset W of Rn is said to be, its definition is closed under vector addition, if whenever we take two vectors in that set W and you add them together, their sum is in W. This set of vectors W is said to be closed under scalar multiplication. If you take any vector, V, in W, you multiply it by scalar R, you get something that's in W. So closed under vector addition means take two vectors from the set, add them together, and the sum is in the set. Closed under scalar multiplication means take any vector in set W, multiply it by any scalar, and the result is in set W. And those are the two things we do to vectors. Add them together and multiply them by scalars. A subset, non-empty subset of vectors from Rn is called a subspace of Rn if it's both of these. It's both closed under vector addition and closed under scalar multiplication. Now, what do you call it when you combine vector addition with scalar multiplication? That's the L word, linear. You're taking linear combination. So we could, if you like vocabulary, rewire this to say, well, closed under linear combinations means both of these types of closures. So a subspace is a non-empty subset that's closed under linear combinations of its elements. Okay. We'll maybe occasionally deal with these two together and discuss linear combinations. Here in the beginning, we'll look at questions about, which we're about to see, questions about subspaces and address them in terms of these two things separately. Closure under vector addition and closure under scalar multiplication. Let's do so. Okay. Here's your set of vectors. Take all vectors of R3 of the form 2x, comma, x plus y, comma, y, where x and y can be any real numbers, our set notation we introduced earlier. Okay. So some examples of vectors in this set are 2, 1, 0. Take x to be 1. Y equal to 0 gives you 2, 1, 0. Take x to be 0 and y to be 1, it gives you 0, 1, 1. So you just choose different values for x and y and they produce different vectors. That's the kind of vectors that are in set W. It's a subset of R3 because the vectors have 3 components. The question is determine whether it's a subspace of R3. Okay. Definition we just saw says we need to check for closure under vector addition and scalar multiplication. So you take yourself 2 vectors, let's call them V1 and V2, in this set of vectors. Do you know what they look like? Yeah. The first one is 2 times some x value, let's call it x sub 1, x sub 1 plus y sub 1 for some y value, comma y sub 1. There's an x1 and a y1. that determine this vector v sub 1, because that's the kind of stuff that's in set W. The second vector, similarly, there's some x's and y's. Let's denote them x sub 2 and y sub 2. So that's why the choice of the subscripts. And that second vector is of this form. We're trying to test, I guess, first for, I see it in the shadows, vector addition. So we'll add v1 and v2 together and see if there's an x and y that produces that vector sum. Okay. v1 plus v2, I know what v1 looks like. I know what v2 looks like because I know what everything in W looks like in terms of maybe a format. You give me x and y, I'll give you a W. I give you a W, you can probably find the x and y as well, reverse engineer it. All right, add those together, you add them component-wise. Here's the sum. I tell you what, let's rearrange that a little bit. Trying to make it look like this if I can. I want to see 2 times something. Second component, I want it to be something plus something else, and then I want the something else on the outside. So I want to see 2 times here. I want to see a term here. And in the center, I want whatever 2 is multiplied by here and whatever that component is appearing here. Is this of the form of the elements of W? Well, let's factor 2 out. We got a 2x1 plus 2x2 from adding the first components. Factor 2 out. And we get 2 times something, which sounds promising because the elements of W are 2 times something. And the something is specific here. What else? In this, well, in the third term, we've got y1 plus y2. I got my reasons. Let's bracket those off as well. And remember what we're looking for. I want to see if the center component is whatever's multiplied by 2 here plus whatever we see there. What's multiplied by 2? x1 plus x2. And I do see an x1 plus x2 here. What's over there? y1 plus y2? I do see a y1 plus y2. So we've taken this and rearranged it, getting the x1 and the x2 together and the y1 and the y2 together. Just numbers. Don't need to justify that, just real numbers. So, indeed, this is of the same form as an element of W. It's 2 times something. Third component is something else. There's the something and the something else added together in that center component. More professionally, it is of the form 2x comma x plus y comma y, where I can tell you exactly what x and y are. They're x1 plus x2 and y1 plus y2 respectively. Substitute those in to here, you get this, and that is v1 plus v2. v1 plus v2 is of the right form to be in W. We took 2 arbitrary elements of W, 2 vectors, added them together. They're in W. We have closure under vector addition. All right, let's check closure under scalar multiplication. It's a little bit easier, just multiply a vector by a scalar. Process is fairly similar though. Take a scalar R. Let's multiply it by, say, vector v1, the one we just had. I don't need 2 vectors to check this part. Okay, we had v1 written in terms of components as given here. We'll take that R, multiply it by each of the components, not distribution. Producing this, that's how you multiply by scalars. All right, now we want to see if this is in the form of an element of W. So as in the previous one, trying to make this, if I can, look like that. This starts out 2 times something. Okay, let's rearrange this first component to read 2 times something. It's 2 times scalar R times number x sub 1. How about we distribute here and get R times x sub 1? You know, actually, I want to see right there whatever we have sitting here. I'll get 2 times something. I want to see the something there. Third component is R times y1. I can bracket those off if you like. I'm trying to match up pieces. And indeed, we can get R times y sub 1 there. So distributing in this second component produces this. And this is of the exact same form as elements of W. We've got 2 times something. That something we'll call x. It's R times x sub 1 in our symbols. The something else, my new vocabulary ideas. The third component is R times y sub 1. And you get those 2 added together in the middle, You do. Then that's a vector in subset W. And scalar times vector V is in W. W is closed under scalar multiplication. We needed two things to have a subspace. Closure under vector addition, done, previous slide. Closure under scalar multiplication, done, this slide. So indeed, this is a subspace of R3. Okay, back to the notes. Subspace property. Okay, we're working our way towards a definition of a basis of a space and a basis of a subspace. Theorem 1.14 says, let W be a span of the vectors W1 through W sub k. Then the claim is W is a subspace of Rn. So they're claiming that spans of non-empty sets of vectors are subspaces. Okay, so one way I could give you a vector space is give you a basis. According to this, I could also give you a vector space, well, a subspace of Rn. That's the only kind of vector spaces we've dealt with so far, by giving you a spanning set. Though we haven't formally defined basis, basis and spanning sets have a fairly intimate relationship, though they're not exactly the same. These vectors that generate this, well, that's the word I'm defining. These vectors W1 through W sub k are said to span or to generate the subspace. Does this make any sense? Well, yeah, we took spans by taking all linear combinations because that's what you do with vectors. To generate means the same thing. Do what you do with vectors. And what you do with vectors is take linear combinations of them. Well, that's why the class is called linear algebra. All right, so claim is that a span of a set of vectors is a subspace. So what was a subspace? Subset of vectors, it was closed under vector addition and scalar multiplication, the two things we do to vectors. All right, let's go through the proof of that. Because it really does illustrate the ideas. And it's not very difficult, this one. It's almost computational. Okay, so we want to show that we've got closure under vector addition and scalar multiplication. That's how you show something is a subspace. The claim is, then we've got a subspace of Rn. Okay, so take you a couple of vectors that are in the span. Here, that set of vectors, W is a span of these vectors. Take a scalar, let's call it C. All right, can you tell me what U looks like in that previous example? Well, it's in the span of these vectors, so U is a linear combination of these vectors. U is of the form R1W1 plus R2W2 up through R sub k W sub k. For some scalars, R1 through R sub k, because that's what the span of this set of vectors is, the collection of all linear combinations. Well, one of them linear combinations must be vector U. That's how it got in the span. Similarly, vector V must be some linear combination of the vectors W1 through W sub k as well, because it's in the span. That's what span means. So I do know the form of U and V by knowing that they're in this span. Now we need to first add them together and see if it's in the span. How will you be able to tell if it's in the span? Because the sum U plus V will be a linear combination of W1 through W sub k. All right, V plus W, we know the form of, U plus V, we know the form of U, we know the form of V. Okay, we're trying to, what are we trying to do? Trying to see if this vector sum is a linear combination of W1 through W sub k. Well, there's a W1 and a W1. Let's use our properties of vector addition, commutativity, and associativity to move some things around and write this as, I'm boring of doing things at this grotesque level of detail that we may have earlier. So let's skip a few arithmetic steps because they're becoming familiar. Factor W1 out of these two, that'll leave us with an R1 plus S1. factor W2 out of this term and this term, R2 plus S2 times W sub 2, and so forth. Up through the last term, factor W sub K out, and we get, dude, it's a linear combination of W1, W through 2 through W1, W2 through W sub K. Here's the coefficients, R1 plus S1, R2 plus S2, R sub K plus S sub K, respectively. Okay, anyhow, it's number times W1 plus number times W2, blah, 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 number times W sub K, linear combination. Oh, well, if it's a linear combination of W1 through W sub K, then it's a vector that's in the span, because the span is a set of all linear combinations. So U plus V, in fact, is in the span, and this spanning set's closed under vector addition. Next slide will be closure under scalar multiplication. What you're going to do, take one of these vectors, multiply it by a scalar, and see if the result is a linear combination of W1 through W sub K. Okay, let's take C times vector U. We knew what vector U looked like. It was the one, I guess, with the R's as coefficients. We distributing here? Yeah, it's distribution of scalar multiplication over vector addition. So distribute the C over that sum, producing something of this sort. All right. Hey, that's a scalar times W1 plus a scalar times W2 plus a scalar times W sub K. Again, we distributed and I grouped together in a single step. That's the vector in the span of W1 through W sub K. This is a linear combination of those vectors. We've got a vector then in the span, arbitrary scalar, arbitrary vector. We've got closure under scalar multiplication. That's the two things you needed. That's the two things you got. So this spanning set, in fact, is a subspace of Rn. So spans of sets of vectors are subspaces of Rn as given. Where we have as a subspace a collection of vectors from Rn that's closed under what? Well, linear combinations, vector addition and scalar multiplication. Let's illustrate it. Okay, find a generating set. Okay, it'd be like a spanning set, eh? For the solution set of the following homogeneous linear system. Okay, let's see. We've got what, 4 unknowns and 3 equations, homogeneous. Right-hand sides of all the equations are 0. You take differential equations, you'll run across a homogeneous linear differential equation in DEs as well. It's related to this. That may not be immediately obvious when you first encounter it, but it's related to the idea with the zeros here in some sense. Okay, let's make an augmented matrix and use Gauss-Jordan elimination. Make the augmented matrix. What's going to happen? Just going to have a unique solution? If it had a unique solution, we could reduce this coefficient matrix down to the identity. We know that now. We can't reduce this down to the identity. It ain't even got the right dimensions. So it won't have a unique solution. Hey, is it consistent? Yeah, it's homogeneous. I can take x1, x2, x3, and x4 all to be 0. So of course it has the trivial solution. I'm practicing my vocabulary with you. Are there other solutions? Well, we're going to get free variables. You're going to have to get free variables because there ain't room for every column to contain a pivot. So I know there'll be a free variable. My first guess would be, we're getting experience with this, the free variable will probably be x sub 4. That's not necessarily true, but this technique we do preferentially pushes those free variables kind of down the list, pushes them to the right because of the way we do the row reduction. So I suspect, my first guess is it's x sub 4. I shouldn't be so liberal with my prediction. So it depends on how the numbers come out. But there's definitely a free variable because there ain't room but for 3 pivots. Okay, we'll use the 1 to eliminate the 1 down here. That arithmetic's done. First column's good. These are nice numbers. So we won't mess with the first column anymore. We'll move down and to the right. Got a pivot there. Let's use that 1 to eliminate that -1 and that 3. Okay, so we'll add row 1 plus row 2 to take care of the first row. That'll get us a 0 there. We'll take row 3 minus 3 times row 2. 3 minus 3 times 1. That'll get us a 0 there. Some other arithmetic happen. Still encourage you to practice these, because these are all pre-typeset. It's easy to mess up the arithmetic. These are also very many times proofread. What's next? First row and first and second columns are good. First column's good. Second column's good. Down and to the right. Ooh, you want to divide that by -5? I guess so. We're at least temporarily seeing some fractions. Nothing else I can do. I'm not going to mess with anything I've already got fixed. So now it's a matter of fixing, if I can, the third column, or if you like, fixing the third row. So I really got no choice but to divide by -5. Okay, some fractions popped in, but now I can use the 1 to eliminate that 1 and the 1 to eliminate that 2. And we'll have the first 3 columns just fine. And sure enough, there's gonna be a pivot-free column corresponding to a free variable. Okay, here's where we left off. Do the usual subtraction. It introduces some fractions. And how we doing? Pivot, 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 pivot-free column. So the coefficient matrix, there's one pivot-free column, there's one free variable. As is now hopefully routine, let's take the augmented matrix, turn it back into a system of equations. Rewrite that as x1 equals x2 equals x3 equals x4 equals. I don't know what x sub 4 is, so I'll just call it x sub 4. It's a free variable. We'll actually make that substitution. Let's let r equal x sub 4 be a free variable. You got a better idea? You know, these all have denominators of 5. We could have let r equal x sub 4 divided by 5. That's an arbitrary real number too. And we could hide this division by 5. We pick up a multiple of 5 down here. The book will do that in their solutions. And eventually I'll start doing that as well, because I don't like fractions. I can hide them. It's not like they're not there. I can hide them away in terms of this free variable sometimes. But I'll go ahead with the more obvious way of doing this, unless we got to do something with these fractions. It's just a matter of writing all the stuff down and bookkeeping, really. We'll let r equals x sub 4 be a free variable. Then we've got r times -3/5 for the first component, -4/5, 4/5, and 1 for the components of a vector. So a solution x of that original homogeneous system of equations must be of this form, where r is some real number. This is, if you like, it's all scalar multiples of this single vector. Hey, that means it's the span of this vector. If I only got one vector, how do you take linear combinations of it? Well, I can add it to itself, which is really just multiplying it by 2 if I add it to itself. Or I multiply it by scalars, which takes care of the vector addition. When you've got one vector, taking linear combinations of it or taking a span of a single vector is just multiplying it by a scalar. Addition doesn't do anything that scalar multiplication can't do. So we could say a generating set is given by that single vector. There's an answer. Here's a little bit more details. We could have done this with a different free variable, the x sub 4 over 5 thing. That would have effectively multiplied all these components by 5. Well, it gets rid of the fractions. Notice it changes the last one from 1 to 5. Same manipulations. The book will do that when you look in the solutions manual or the back of the book. You may have done it this way. You look in the back of the book and they've given this answers. There's some numbers that are similar, but they're different factors for sure. Yeah, but they're both valid answers to the question asked. Both of these are a generating set for the solutions to that system of homogeneous differential equations. Sorry, homogeneous system of linear equations. Forgot where it was. Back to the notes. Okay, we're going to associate some vector spaces with a matrix. We're going somewhere with this. Right now, it's just a thing we can do, justified by the fact that, by Theorem 1.14, spans of a set of vectors is a subspace of Rn. These are themselves vector spaces, as we'll formally define them in chapter 3 before we totally formally define them. But we're getting spaces when we take spans of sets of vectors. So we're going to take a matrix and use its row vectors and its column vectors to make some spaces. Given an m by n matrix A, the span of the row vectors of A is called the row space of A, and the span of the column vectors of A is called the column space of A. Using the row vectors, using the column vectors, we can make two different vector spaces. We can consider yet another vector space. If we'll take all solutions to the homogeneous system of equations, AX equals 0, this will be closed under linear combinations, won't it? Yeah, that's the thing we showed when we added all them H vectors together. So this would be closed under linear combinations, and scalar multiplication we didn't check, but that's true as well. These form a vector space. So call the null space, solutions to this system of equations. Could you find a null space? Yeah, it'd be finding a general solution to this homogeneous system of equations and then writing it in a slightly different way from probably the way we did it in the past. I'd take free variables and replace them in terms of some conversation about spans and coefficients in linear combinations. How about describing row spaces and column spaces? Well, I can give you a spanning set because they are by definition given by a spanning set of vectors. The rows of matrix A form a spanning set for the row space, for example. But that doesn't tell you much. I might be going for a little bit more than just a spanning set. We might want something a little neater. We want a basis. Definition 1.17 says, let W be a subspace of Rn. The subset W1 through W sub k of W is called a basis for W if every vector in W can be expressed uniquely as a linear combination of those vectors. All right, that ain't the definition I like of a basis. We're going to re-see a lot of this stuff in chapter 3 in a more general setting, and that ain't the definition we'll take for basis there. It's equivalent to this, so we're not wandering off in the wrong direction. But here's our definition, finally, for basis. We'll be able to talk about dimension here before it's over with, based on basis ideas. But what's it say? We got a basis for a subspace if every vector in W can be expressed uniquely as a linear combination of W1 through W sub k. It can be expressed as a linear combination. So that means the expressed as, forget the uniquely, expressed as a linear combination, that means it's a spanning set. So what we're getting first is this means W1 through W sub k, the span of that set of vectors, is space W. It's a spanning set. And then some, whatever the implication about the unique linear combination stuff is. I can't hide the truth. It turns out the uniqueness will imply we have a linearly independent set. We define linearly independent recently. So we'll have a linearly independent spanning set. When you hear basis, that's what you're going to want to think. First, let's go through and do another result or two, and we'll get to that concept. Right now, a basis is what they defined it to be, but a basis will be a linearly independent spanning set. I see the spanning set, the linearly independent. Well, this kind of gives that away, actually. Theorem 115, a unique linear combination, says set of vectors W1 through W sub k is a basis for its span if and only if A linear combination of those vectors, set equal to the 0 vector, implies that those scalar coefficients must all be 0. Hey, that was what the definition of linear independence was, in fact. Okay, let's go through the proof of that because it's enlightening, it's supposed to be, and it's not hard. Okay, so these vectors are a basis for their span if and only if we get this linear combination behavior. All right, what's a basis? For now, our definition of basis is unique representations. Also, this is an if and only if claim, so we got to show two implications. Okay, suppose first that W1 through W sub k is a basis, then we want to show this implies this. Secondly, we'll suppose this implies that, and then have to show that that means we have a basis. Okay, suppose we have a basis. That means, by definition, every vector can be written uniquely as a linear combination. That's our definition, 1.17. Whether I like it or not, that's how we're starting with the definition of basis in this particular setting. Okay, so let's see. Let's take the 0 vector. That's certainly in W. That's a span of these vectors. I get that if I take all of the R1, R2 up through R sub k. If I take all those coefficients to be 0, then yeah, we're going to get the 0 vector out. So that is in this spanning set, W. Okay. This says the implication here is if we get 0 out, then those coefficients must be 0. Do we have, certainly if the coefficients are 0, we get the 0 vector out. That's how I know the 0 vector is in W. All right, so take a linear combination, set equal to 0. That's certainly satisfied when all those coefficients are 0. Is that the only time it's satisfied? Yeah. Every vector, including the 0 vector, can be expressed uniquely as a linear combination of the W sub i's. So one way to get the 0 vector out is to use all those coefficients are 0. The hypotheses tell you there ain't but one way to do this in terms of choosing coefficients. So that one way must be choosing all those coefficients to be 0. The implication is linear combination equals a 0 vector. We know we could get scalars to be 0. We must get the scalars to be 0 because of the uniqueness part in the basis. So this part is easier with that uniqueness approach to it. But that shows then if we have a basis, then this equation implies these coefficients. Now we got to turn that logic around and say, suppose this equation implies those coefficients are 0, show you have a basis. That is, show every vector can be uniquely written as a linear combination of these. Just the definitions. All right. Suppose linear combination set equal to 0 means that the coefficients must be 0. Well, take yourself a vector, W vector, in set capital W, and suppose W can be written two different ways. And set W is a span of those vectors, so I know anything in W, the set, like W the vector, can be written as a linear combination of the W1 through W sub k. Suppose you can do it two different ways. That is, with these scalars, C1 through C sub k, and these scalars, D sub 1 through D sub k. All right. Hey, wait a second. What do we know? We know about linear combinations that give the 0 vector. Okay. Well, what if we take W minus W? That'd be the 0 vector, and let's use, for this first W, the representation with the C's, and for the second vector W, the representation with respect to the D's. Same vector, but different representations of it. Well, if I take this minus this linear combination minus that linear combination, do your distribution deal, collect together coefficients of W1, we'll have a C1 minus D1, W1. C2 minus D2, W sub 2, and so forth. All right. Hey, that's a linear combination of W sub 1 through W sub k, and that linear combination gives you the 0 vector. This time, we're assuming the only time that can happen is when all of those coefficients are 0. So C1 minus D1 must equal 0. C2 minus D2 must equal 0, and so forth. Well, that means C1 equals D1, C2 equals D2, and so forth. So these two different representations, they weren't different after all. Turns out they're the same because there ain't but one way to represent a vector W in this set of vectors, capital W. Unique way to represent it, that means it's a basis, because by our current definition, that's what a basis is. All right, let's see if we got a basis here. Use the theorem about bases to determine whether this set of vectors is a basis for the subspace of R2 that it spans. Okay, this is an easy little problem. The computations aren't hard, but there's a big idea behind what we're about to do here. It's going to motivate a bunch of the stuff we do in the future. Okay, it's a basis if, by what we just saw, there's the word span. I need the word span somewhere in here. We're taking the span of these two vectors. If we can show a linear combination of those two vectors equals 0 vector, implies R1 and R2 are 0, then Theorem 15 tells us we got ourselves a basis. If not, if R1 and R2 need not both be 0, we don't have a basis. So that's the plan. Okay, so let's let R1 and R2 be scalars, and we'll take a linear combination of those two vectors, set equal to the 0 vector. R1 and R2 certainly could be 0. Could they be something else? Because this is going to turn in, here it comes, two equations and two unknowns. Do the arithmetic, take the scalar multiples on the components of the vectors, then add the vectors together. Produces negative R1 plus R2, comma, R1 plus 2R2 equals 0, comma, 0. We need these two linear equations to be satisfied. Okay. We could set up Augmented Matrix and go to town, and that's what hopefully your preference is, to keep it to a minimum of typing. It's easy to just, from observation, see what's going on here. We solve for, say, R1 in this first equation, take the R1 to the other side, we get R1 equals R2. Then we can plug that in this second equation and discover that we need R1 to be 0 and R2 to be 0. So there really is a unique solution. You want to set up an augmented matrix and do the row reduction. Good for you. I think that's an excellent idea. If we had more than two vectors, I'd certainly go augmented matrices. But this one is easy to eyeball. And I see we must have R1, R2, both 0. So there's a unique solution to this. Hey, what if there wasn't a unique solution? What would go wrong in those augmented matrices? Pivot-free columns and free variables, and we get multiple solutions. Well, that doesn't happen here, and we've shown that a linear combination equals 0 implies those coefficients must be 0. Theorem 15 tells you then this thing is a basis for what it spans. Their question was, is it a basis for what it spans? Yeah, yes, is a basis for its span. All right, and we'll shift gears a little bit and start looking at conditions on the invertibility of a matrix. Let's take a little break, and I'll come back with a second video for this section on that. And I'll see you shortly with those details. Bye-bye.